aware of the emergent environment, and we aren't directly cognizant of the true degrees of freedom living out there on the boundary.
Well, that's the way emergence works, right? So, this is far from the only example of something being emergent in physics. So, there's an example I like to use, right? So you can't really see, but I have a table in front of me here.
Sure.
And if I knock on the table, I think you can hear it.
Yep. I hear some phonons.
Yeah, you hear some phonons. That's right. So the information that I knocked here, and how hard I knocked is transmitted through the table by degrees of freedom called phonons. They're, lattice or compression vibrations inside of the table. And there's a whole theory of phonons, that condensed matter physicists write down. There's even quantum field theory for phonons. And when you want to answer the question, if I knock on the table here, when do you get a signal over there? Then you should use the phonon theory. Okay. And yet, the table is just some state in the standard model of particle physics with all of, the quarks and leptons and everything. And in the standard model, Lagrangian, in the fundamental description of the standard model, there's no phonon field. There's no phonon particle. It's just some convenient fiction, which you use when you want to answer questions about tables. And if you find yourself in a state, for example, where there is no table, then you're probably not going to talk about phonons. And so the idea is that space-time itself is like phonons. In certain situations, it's convenient to describe things using space-time, but there will be errors in that description that you can see if you do careful enough experiments. And in some situations, it'll just be a totally wrong picture of what's going on.
And for some evolutionary reason, we're aware of the emergent description, but not directly aware, unless you're really smart and do physics, of this more fundamental description.
Yeah, that's right. And that's the way that physics has gone for hundreds of years.
All right,
there's a lot of stuff that you and I know because we have PhDs,
Yeah.
which most people don't know because it doesn't seem very.
All right, okay, listen, look, I don't think physics is hard, right? What makes the entire thing hard is the academic system. Like, it's not hard to know that within this closed system, right, that whether you have A and B, that as we talked about yesterday, that the basis of the core fundamentals of the entire thing will come down to a simple equation. A plus B equals. Now, there's two arguments, okay? There's two arguments within this finite resolution within what is physics and math, right? That A plus B equals, because the answer is A plus B, right? But some people will say that it doesn't equal A plus B. A plus B equals A plus B equals, right? Which equals A plus B equals, right? And this is my opinion of it in entirety, because things have to be recursive, right? To a point. It's like A plus B equals 0 to when point, right? So that has to be incorporated into it. That's why when I think of math, I think of them as recursive, right?
Relevant for their daily lives, and that's fine, right? And of course, I'm not judging, right? That's totally reasonable, right? You should learn the things you need for your daily life first, and it's only when you ask these more refined questions, like, for example, how can we get through life without knowing quantum mechanics? We could have asked that, right?
Right.
Why don't we walk around thinking in